Hello everyone, we are looking at Module 4, Homework A, Tab 1, and this is the first part, and we're looking at speed at separation distance. So we have to find the speed v of r of a small mass, little m, as it falls towards a larger mass, which is denoted by capital M, starting from an infinite separation distance and gaining speed as it moves towards the larger mass. If we know that, I think it tells us, yeah, right here. I don't know why it's so pixelated on my screen right now. It was not like that 5 seconds ago. Given that capital M is much larger than little m, we can assume that the large mass remains in a fixed position and the small mass is falling under the influence of gravity. So we have to understand that this problem involves gravitational potential and kinetic energy. As the smaller mass m moves towards the larger mass, capital M, gravitational potential energy is converted into kinetic energy. And the gravitational potential energy between the two masses, capital M and lowercase m, is going to be at a distance r is going to be given by capital U is equal to minus g times capital M times lowercase m all over r, where g is the gravitational constant, capital M is the larger mass, and lowercase m is the smaller mass, and r is the separation distance between the two masses. And the negative sign tells us that the gravitational potential energy is lower when the two masses are closer together, and we know that gravitation is an attractive force. So let's take a look at the kinetic energy on the smaller mass, m. It'll be Ke is equal to 1/2 times lowercase m, that's not look like a very good m, times v squared, where v is the speed of the smaller mass. So the principle of conservation of mechanical energy states that the total kinetic energy, kinetic energy plus potential energy, remains constant if no external forces other than gravity are acting on the system. And initially, when the masses are infinitely apart, the potential energy approaches zero. So we can think about that as capital U as approaches infinity is equal to 0. At this point, the smaller mass is released from rest, so its initial kinetic energy should also be 0. Thus, the total energy at the start is going to be zero. As the mass, little m, falls towards uppercase M and reaches distance r, the total energy must still be equal to 0, since the total energy is conserved. So we can write E sub r is equal to K sub lowercase r plus U sub r is equal to 0. Substituting the expression for kinetic energy and potential energy at distance r, we get 1/2 times lowercase m times v squared, I don't know why I wrote an equal sign, minus g times uppercase M times lowercase m divided by r should equal to 0. So now let's solve for the speed v of r at the separation distance r. And we can rearrange the following equation to be 1/2 times m times v squared is equal to g times uppercase M times lowercase m all divided by r. And if we cancel mass little m from both sides, we get 1/2 times v squared is equal to g times uppercase M all divided by r. And then now we can go ahead and multiply both sides by 2. So now we're left with v squared is equal to 2 times g times m all over little r. And finally, we have to take the square root, which leaves us with v of r is equal to the square root of 2 times g times uppercase M all divided by r. And that is our final answer. And this shows that the smaller mass gains speed as it falls towards the larger mass, with the speed increasing as the separation distance r decreases.